In everyday use and in kinematics, the speed of an object is the magnitude of its velocity. It is thus a scalar quantity. The average speed of an object in an interval of time is the distance traveled by the object divided by the duration of the interval. The instantaneous speed is the limit of the average speed as the duration of the time interval approaches zero. Like velocity, speed has the dimensions of a length divided by a time. The SI unit of speed is the metre per second, but the most usual unit of speed in everyday usage is the kilometre per hour or, in the US and the UK, miles per hour. For air and marine travel the knot is commonly used. The fastest possible speed at which energy or information can travel, according to special relativity, is the speed of light in a vacuum. C equals 299,792,458 meters per second. Matter cannot quite reach the speed of light, as this would require an infinite amount of energy. In relativity physics, the concept of rapidity replaces the classical idea of speed. Definition: the Italian physicist Galileo Galilei is credited with being the first to measure speed by considering the distance covered in the time it takes. Galileo defined speed as the distance covered per unit of time. In equation form, this is where v is speed, d is distance, and t is time. A cyclist who covers 30 meters in a time of 2 seconds, for example, has a speed of 50 meters per second. Objects in motion often have variations in speed. In mathematical terms, the speed v is defined as the magnitude of the velocity v, that is, the derivative of the position r with respect to time. If s is the length of the path traveled until time t, the speed equals the time derivative of s. In the special case where the velocity is constant, this can be simplified to v equals st. The average speed over a finite time interval is the total distance traveled divided by the time duration. Instantaneous speed: by looking at a speedometer, one can read the speed of a car at any instant, or its instantaneous speed. A car traveling at 50 km per hour generally goes for less than 1 hour at a constant speed, but if it did go at that speed for a full hour, it would travel 50 km. If the vehicle continued at that speed for half an hour, it would cover half the distance. If it continued for only 1 minute, it would cover about 833 am. Average speed: different from instantaneous speed, average speed is defined as the total distance covered over the time interval. For example, if a distance of 80 km is driven in 1 hour, the average speed is 80 km per hour. Likewise, if 320 km are traveled in 4 hours, the average speed is also 80 km per hour. When a distance in kilometers is divided by a time in hours, the result is in kilometers per hour. Average speed does not describe the speed variations that may have taken place during shorter time intervals, and so average speed is often quite different from a value of instantaneous speed. If the average speed and the time of travel are known, the distance traveled can be calculated by rearranging the definition to. Using this equation for an average speed of 80 km per hour on a 4-hour trip, the distance covered is found to be 320 km. Expressed in graphical language, the slope of a tangent line at any point of a distance-time graph is the instantaneous speed at this point, while the slope of a chord line of the same graph is the average speed during the time interval covered by the chord. Tangential speed: linear speed is the distance traveled per unit of time, while tangential speed is the linear speed of something moving along a circular path. A point on the outside edge of a merry-go-round or turntable travels a greater distance in one complete rotation than a point nearer the center. Traveling a greater distance in the same time means a greater speed, and so linear speed is greater on the outer edge of a rotating object than it is closer to the axis. This speed along a circular path is known as tangential speed because the direction of motion is tangent to the circumference of the circle. For circular motion, the terms linear speed and tangential speed are used interchangeably, and both use units of ms, kilometre per hour, and others. Rotational speed involves the number of revolutions per unit of time. All parts of a rigid merry-go-round or turntable turn about the axis of rotation in the same amount of time. Thus, all parts share the same rate of rotation, or the same number of rotations or revolutions per unit of time. It is common to express rotational rates in revolutions per minute or in terms of the number of radians turned in a unit of time. There are little more than 6 radians in a full rotation. When a direction is assigned to rotational speed, it is known as rotational velocity or angular velocity. Rotational velocity is a vector whose magnitude is the rotational speed. Tangential speed and rotational speed are related. The greater the RPMs, the larger the speed in meters per second. Tangential speed is directly proportional to rotational speed at any fixed distance from the axis of rotation. However, tangential speed, unlike rotational speed, depends on radial distance. For a platform rotating with a fixed rotational speed, the tangential speed in the center is 0. Towards the edge of the platform, the tangential speed increases proportional to the distance from the axis. In equation form, where v is tangential speed and I per mil is rotational speed. One moves faster if the rate of rotation increases, and one also moves faster if movement farther from the axis occurs. Move twice as far from the rotational axis at the center and you move twice as fast. Move out 3 times as far and you have 3 times as much tangential speed. In any kind of rotating system, tangential speed depends on how far you are from the axis of rotation. When proper units are used for tangential speed v, rotational speed I per mil, and radial distance r, the direct proportion of v to both and I per mil becomes the exact equation. Thus, tangential speed will be directly proportional to a when all parts of a system simultaneously have the same I per mil, as for a wheel, disk, or rigid wand, units. Units of speed include, meters per second, the SI-derived unit. Kilometers per hour. Miles per hour. Knots. Feet per second. Mach number, speed divided by the speed of sound. In natural units, speed divided by the speed of light in vacuum. Values in boldface are exact. Examples of different speeds. Vehicles often have a speedometer to measure the speed they are moving. See also. References: Richard P. Feynman, Robert B. Layton, Matthew Sands. The Feynman Lectures on Physics, Volume I, Section 8-2. Addison Wesley, Reading, Massachusetts. ISBN 0-201-02116-1.